Okay, so I get to talk to you about fluid interfaces, and here's the outline of what I wanted to go over during our time together. First, I wanted to talk about a subject which is more classical, really. It's this idea of surfactant molecules, molecules that have some non-polar part and some polar part that accumulate at fluid interfaces and that can change the mechanics of those interfaces. And this is a classical subject, and there's two sort of modes of how people think about small molecule surfactants and how they can change dynamics. One is thinking about surface viscosity, and the other is emphasizing the dependence on surface tension. And so the first two lectures are going to be about these ideas. What does it mean for just very simple problems of translating drops? Why would we care? How does it help select length scales for drop breakup modes, etc.? Okay. And then I wanted to move on to my next lectures will be about issues that have to do with particles being located at fluid interfaces. And so what happens when we have a particle that can become trapped in an interface? How can those particles interact and make structures? And how do they interact, for example, with the underlying shape of the interface? So that's the whole goal. That's the whole goal of my 4 hours. And today we're going to focus on this issue, just surfactants and hydrodynamics. And so I'm going to start just with a bit of a historical perspective of just, so these are the aims of today's lectures, to understand, I'd like to turn this into a pointer. There we go. To understand stresses at fluid interfaces with a focus on surface tension, to think about how surface tension depends upon composition, and how does this translate into nonlinear and sort of rich behaviors that you can have on moving drops and bubbles. And eventually to talk about work that has to do with drop breakup modes, and then still some open questions in this field. So, so common boundary conditions. We are used to talking about no slip at solid surfaces. Increasingly now we talk about slip at solid boundaries. We are used to at fluid interfaces discussing continuous velocities, continuous viscous stresses, and normal stress jumps. And so we would typically look at some stress condition at a fluid interface of this form. And the question is, what else happens? And so this all started, in a sense, many years ago, when the Hadamard-Brzezinski solution for the steady translation of a spherical drop became known. And so it's a very simple expression that says the terminal velocity of the droplet is equal to some factor times Stokes' terminal velocity times some function of the viscosity ratio. And if the viscosity ratio tends to become large, then we recover a factor that puts us right back at Stokes' flow. And I'll give you all my slides later, so just take notes if it helps you concentrate. And so this was a natural problem for people to go and do experiments, and these are centuries old, and it wasn't obeyed. And in particular for small drops or bubbles, they moved as if they were little rocks. And so there was some extra dissipation in the system. This was true even for bubbles when the viscosity ratio was negligible. And so this very simple and testable idea just failed. And there were two camps, in a sense. Well, the first camp emerged immediately. Was Boussinesq had this insight that we've accumulated something at the interface, or there's some special mechanics in this transition zone, and there's some viscous dissipation in that zone. And so with that idea, he said we can reconcile this. If the fluid interface itself is dissipating, and that wasn't accounted for in this simple model using continuity of stresses, then that could explain this discrepancy. And so actually Boussinesq formulated, assuming a dilatation viscosity, that at the top of that droplet, that nice spherical droplet, there's a strong dilatation at the leading pole, and strong dilatation at the bottom pole. And that dilatation, that stretching of the interface, could be resisted by some in-plane viscosity. And so we can even think about, here it is for a planar interface formulated by Scriven. He said, look, if I had a stress, some viscous stress discontinuity at a planar interface, we could think about some gradients in surface tension, some viscous dissipation in the layer because of dilatation in the layer, and some shearing in the layer. So there's that formulation, and there are many things that absorb at interfaces and that form structures, and that have not just viscous dissipation in the layer, but viscoelastic behavior in the layer. And so that thought process set this field of surface rheology off and running. Okay, so that's one mode of thinking. And the other mode of thinking was proposed by Frumkin and Levitch in a paper in 1947. So Frumkin was a famous electrochemist, and he had done a lot of work on things like mercury droplets and looking at using them as electrodes. And he was thinking about adsorption and surfactancy. And so this was a natural partnering between Levitch, who focused on physical chemistry of various interfaces and boundaries. And they said, perhaps we've underappreciated the role of surface tension in this problem. That if you look at a Gibbs formulation for an interfacial tension, that the surface tension changes because of excess entropies in the layer coupled to temperature, but also because of anything that adsorbs on the interface. And surfactants, small molecule surfactants, are molecules that have a polar part and a non-polar part. They're designed to adsorb on an interface. And they said, perhaps we could, by understanding this dependence better and understanding what is adsorbing as a function of bulk concentration, we might understand the source of dissipation here. And so the idea that they had was that let's suppose molecules are being supplied from solution to this droplet. And so they're adsorbing on the interface, being convected by surface convection, desorbing, and they can diffuse away. If up here we've depleted, we can diffuse toward the interface. If down here we've accumulated, we can diffuse away from the interface. And so if that transport, that mass transfer to and from the interface is slow compared to surface convection, then you can accumulate molecules at this trailing pole. And if you accumulate molecules at this trailing pole, surface tension here will be low, surface tension here will be high, and the surface will pull in the opposite direction of the surface flow. That's the story. And the reason that this was interesting, and both can be present, but there are many systems in which surface viscosities are negligible, and these systems are present. And because they're so tightly coupled with these rates of transport, that we can select concentration regimes and molecules to get different behaviors. And so that's why I'm going to focus on this discussion today. And I'm going to tell you this story about how you can manipulate these Marangoni stresses. That's the name of the surface tension gradients. They're named after Marangoni, somebody has unearthed his original works from centuries ago. And and he's implicated in Tears of Wine, which we can discuss at the reception. But this concept of low tension pulling toward high tension is a Marangoni effect. And for translating droplets, it's going to be a bit boring. It's going to be much better when we get to the second half. But bear with me, because it gets so good at the second half. Okay. So if we think about now a stress balance in an interface, and here I've got just a pressure jump over a curved fluid interface, viscous stress jump. Here I have mean curvature times surface tension balancing normal stresses. Here's my Marangoni stress, my non-uniform tensions balancing that, which are occurring because of concentration gradients. And here I just sort of lumped in, I didn't go through the work of properly posing tensorially all the terms that I'm about to throw out. This is a term for a surface viscous terms, and there are other surface viscous terms that would appear. And so if we were to say, what's my characteristic scaling, let's just think about the viscous stresses. They're going to scale as mu, my prevailing velocity. Suppose I have a buoyant droplet, for example, divided by the length scale of the droplet, the radius, The Laplace pressure is going to scale as the surface tension over the radius. Here, the surface tension, we think of a chain rule. Let's think about isothermal droplets. Thermocapillarity could be for another day. And so we would just think of this as a chain rule, that I would take some derivative of surface tension with respect to composition and some characteristic packing on that interface of excess moles per unit area divided by A. And this would be a surface viscous term. And if I divide through, I can get dimensionless groups from my system. I'll have a capillary number, so how deformable is my droplet? I'll have a Marangoni number, which I can also think of as the product between, as an elasticity number, the derivative of the surface tension with respect to composition times the excess moles per area divided by some reference tension, and a Boussinesq number, so how important are surface viscosities. And we're going to think about ignoring surface viscosities and focusing on small molecule surfactants. And so now we have to resort to some discussions of thermodynamics. What is this? And what's interesting is this is a very nonlinear coupling. And because it's so nonlinear, even in the simplest models that we can do anything with in closed form, the nonlinearity allows us to tune behaviors in and out. And so I'm going to go over just some very simple ideas for equilibrium relationships, some very simple experiments to extract transport coefficients, and then discuss their effects in hydrodynamics. So surfactants. I'm interested, so any molecule, surfactants is a made-up word, surface active substance. And different camps use the term in different ways. So when I'm discussing surfactants today, I'm thinking about small molecules which have negligible surface viscosities and can adsorb and desorb fairly readily from interfaces. And there's a large number of surfactants that do many, many interesting things, which I'm not going to address. So for example, insoluble monolayers of surfactants. I'm not really addressing anything that we would study in a spread Langmuir trough. And those are very beautiful. They can form a number of different organized structures. Those are not the focus today. I'm thinking about molecules we can throw into a solution, and then we could do things like make a pendant drop and measure their surface tension evolving over time. And these molecules are very often used in chemical processes to regulate surface stresses for example, making froths or foams or emulsions, etc. Okay? And so the idea is that we have some non-polar group and some polar group, and they partition to fluid interfaces to keep their polar group, for example, in water, and their non-polar group in air or in oil. The polyethoxylated surfactants shown here, or SDS, certain Gemini surfactants with double head groups, bridge surfactants, Triton X100. There's a whole host of commercially available surfactants that are used to regulate stress conditions. And very often formulators know the tricks that I'm talking about today, but not really the scaling arguments behind how they work. So, so the first is to think about just molecules adsorbing on an interface. And so if we just look at the simplest of kinetic theories, we could think about molecules being adjacent to an interface, having some collisional frequency with that interface. And so that would be this parameter beta. Beta C infinity would be a collisional frequency. And they would come onto the interface if there's room. So let gamma infinity be the maximum packing of molecules on the surface, or the minimum cross-sectional, think of it as 1 over the minimum cross-sectional area of molecules in the layer. And so we can adsorb if there's room on the interface, and we can desorb first order in what's adsorbed. And if there are, for example, enthalpic interactions in the layer, we can also have hindered desorption fluxes because of those enthalpic interactions. And at equilibrium, adsorption and desorption have to be equal. So at equilibrium, we could equate these, and we could get an equilibrium isotherm. So these are just simple formulations from a kinetic theory. And if this non-ideal interaction parameter is negligible, we just get what looks just like a Langmuir adsorption model, but here derived from a kinetic point of view, not relying on adsorption sites, but just on this being a monolayer. So in Gibbs' treatment of an interface, there's a relationship which is basically a two-dimensional Gibbs-Duhem equation for the interfacial layer. And it constrains relationships between changes in surface tension, surface excess moles of surfactants, and the chemical potential of the surfactant in solution. So this is a constraint that arises from thermodynamics. And so once we have a partition law that says that given some surfactants in solution, I will have this many molecules pop onto the interface. Once we've got this, we also have the surface equation of state. They're constrained together. They're not independently modelable entities. So if you understand your equilibrium, then by working with the Gibbs adsorption equation, you can do something to infer your adsorption, and vice versa. But this is this quantity, surface tension as a function of surface excess in the layer, is what we were after to talk about that mechanics. We have to couple surface tension to composition. And this is the thermodynamic law that does it. And so, for example, if we were looking at the normal stress jump, which has the mean curvature times the interfacial tension, this is the quantity which would couple us. And if we're looking at the Marangoni stresses, it's the derivatives of this quantity that would couple us. And it's not linear. And I make this point because there are hydrodynamicists who do a beautiful job wrestling with very complex settings and doing very elegant, honoring the hydrodynamics to its nth degree, and then study surfactant effects assuming that it's a 2D ideal gas, which would be valid in the most dilute concentrations. Strictly speaking, if you wanted to relate this to what's known about insoluble layers, a two-dimensional ideal gas ends when molecules are close enough together, lying in an interfacial plane, that their tails can start to come in contact, in which case they leave an ideal gas state. Okay. So taking the asymptote here, well, this is, because I'd say it's non-linear, but it's not horrible. It's not like we can't work with it. Right? So taking a two-dimensional ideal gas approximation and looking at any systems that give large displacements in surface coverage is fraught with danger. In particular, I say that it's very interesting because this would appear in the normal stress jump, and it has this logarithmic singularity, but it's its derivative that appears in tangential stress jumps, which has this first-order pole. And so this has in it, now we are also stuck with trying to reconcile this with data. So I'm going to show you how do we try to reconcile this with data. We have partition laws. This is essentially an isotherm is saying, if I put this many surfactants in solution, how many go to the interface? It's a partitioning law. And it depends upon this. I need to understand something about maximum packing. I need to understand something about this tendency to partition beta over alpha, an adsorption kinetic constant over a desorption kinetic constant. They're fixed at equilibrium. And if I allow myself this third parameter, this is another parameter which would be fit to this equation. So it does come down to some piece of curve fitting to try to reconcile to data. And so this is commonly done by using a pendant drop or a pendant bubble. So here it's a study at air-water interfaces. And so this is now just, you buy these. When I was a student, you built them and aligned them. But it's the simplest of ideas. My mom taught ballet. This is a drop. Can you tell? Okay. So surface tension would like the drop to be spherical. And gravity, I'm buoyant, say. Gravity would like to elongate. And so that shape is just captured by the Young-Laplace equation. And so you take a picture of the bubble, and you digitize the image, and you reconcile it to solutions of the Young-Laplace equation. That's all this is. And you can do that by changing the amount of surfactant in solution, and we can vary that over orders of magnitude, and we can get graphs that look like this. So here's a bubble that was formed at a system that was dilute enough that the tension there is quite similar to that of a surfactant-free surface. And then the concentration is increased over orders of magnitude, and the surface tension reduces at equilibrium. So I'll call that two things. One of them is that then it's fit. I'm not glorifying it. And that these are the kinetic, we can extract from this among other things, a maximum packing, a partition law, and I'll give you the other constants shortly. There are other things here that we can see immediately are not just that, they're just to guide your intuition. If you look at this Gibbs-Duhem equation for the surface, the Gibbs adsorption equation, and we think that what it's doing is it's telling us that the slope of this is ultimately related to the surface excess. So this is assuming that we only have surface excess of surfactant, no other adsorbing species, so we got rid of the sum. And so we look at the slopes here, and we go from quite shallow slopes to steeper slopes that change very, very, very slowly in the high concentration limit. So this is, the data is telling us, regardless of fit, that these molecules are coming to the interface, and eventually they're approaching some maximum packing, that the surface excess is approaching some value from below, and that it's not increasing steeply in the high concentration limit. So that's one thing the data tell you without resorting to any modeling. The other is that at concentrations, at some concentration, we get these sharp breaks, a plateau. And that's because here we had been approximating our chemical potential of our surfactant as an ideal solution. So that's what this is. And that this becomes highly non-ideal at this region. And what's happened is that rather than continuing to put more surfactants in solution, you don't get more monomers. You put in more surfactants, they aggregate to form micelles. Micelles are well-defined thermodynamic quantities with aggregation numbers, and add more, get more micelles. The concentration of monomer stays roughly fixed. Okay. So another thing I'd say is that often people do sort of quick and dirty studies, and they say, well, you know, I'll just use some dynamic methods, and I'll look at them at sort of longish time scales, and I'll guess I had equilibrium. And it's bad. It's bad for guiding thinking because, for example, here's data taken by maximum bubble pressure method trying to make it very, very slow, and it really doesn't capture the equilibrium of this surfactant that you would get by looking at long time asymptotes dependent rocks or Wilhelmy plate methods. Okay. So from the equilibrium, we also fit that partition law, beta over alpha, and the interaction K. And given that, now we can think about dynamic surface tension. And the idea here is just this: form an interface that has no surfactants. So rapidly, for example, form a bubble in solution, and let molecules start to adsorb onto that interface. As they adsorb, the surface tension is going to evolve and eventually come to some equilibrium. So think about T equals 0, clean interface, boom. First we have to adsorb in order to create some depletion, and then we have diffusion toward the layer. And at long times, adsorption is equal to desorption into a uniform sublayer. And so we can think about surface tension versus time as the evolution of the surface concentration versus time. This really requires that surface tension very rapidly reflects the state of the surfactant that is absorbed there. And so again, for small molecule surfactants, these are extremely fast time scales, and so it's a fine assumption. But for molecules like proteins or macromolecules that can meander into many different states on an interface, this fails miserably. And so you'll have to be careful whether or not you're applying an argument of local equilibrium where it can't apply. Okay. So typically, the surface concentration is just inferred by assuming that the surface tension rapidly reflects the instantaneous concentration. There are experiments, for example, Colin Bain has done ellipsometry on dynamically evolving interfaces by having set up geometries where he had a falling sheet over the edge of a trough where he could look at the interface at a steady state, but not at equilibrium. There are other experiments where people have taken pendant drops, and they've let them come to equilibrium, and then they've squeezed and expanded them rapidly compared to mass transport in the system. And there you can see that there's some equilibrium relationship chased out. So it's not just hoping and praying, but it is simply, I want to emphasize that these relationships all rely on local equilibrium, and if you have something else going on, you're going to be inferring incorrect information. So within that assumption, then this just comes down to making a simple model, and these are usually set up to be the world's most simple experiments, just to isolate just what's happening with these molecules, what's their adsorption, desorption, and diffusion. And so a pendant drop or pendant bubble experiment, boom, you form it, and you take pictures over extremely long time scales. There's a weak displacement of the surface as tension drops. The droplet elongates or bubble elongates. And you can do analysis to show that that's not an important correction in the dynamics. But these are set up to be as static as possible to be able to infer these transport coefficients. So here's some results from a very nice paper by Pan, where he'd looked at surface tension relaxation for some surfactant as a function of several different concentrations. And he also took these same systems and he rapidly, so for example, he took one that equilibrates around 60-ish, and he then compressed his surface, dropped his surface tension well below its equilibrium, and watched desorption restore equilibrium. And so from these experiments, adsorption for the forward path, desorption for the reverse, just perturbing this system, and then thinking about the mass transfer, you can get the transport coefficients. So, if you do a dimensional analysis on these systems, you're stuck with the kinetic constants. Those are some result of your chemistry. So there's some collisional frequency, and then that's the beta, and then the alpha is, can I get out of the interface? And I can get out of the interface if I don't love it completely, right? And so this is it's a chemistry question and a structure question. But diffusion to the interface is a much simpler question. You form an interface and you dilute the space under it. And if you think about just a simple problem of, say, an infinitely planar interface, in an infinitely deep system, and you ask, how much can the interface deplete anyway? And so if you just do a little mass balance, take an area element, and the adsorbed mass is gamma equilibrium dA, and then say how deep below that area element did I have to go to find enough surfactant to supply that region. So that would be some volume times the bulk concentration. And if I equate those two, I've got an implicit length scale in the system. It's an adsorption depth. It's just the ratio of the surface concentration over the bulk concentration. After I've said it, it's really obvious. And if we were to think about truly a planar system, that the diffusion timescale for that infinitely deep system would be this length scale squared divided by d. If we have curved layers, then it becomes slightly more complex. One of these length scales becomes the radius of the droplet, for example. But for a planar system, we can define this diffusion timescale. And if I scale, for example, surface tension relaxation versus time, let me go back one. So if I take, for example, surface tension versus time, and I rescale that time scale with the diffusion time scale, I can collapse these layers significantly. Not all of them collapse as beautifully as this one. If I have significant adsorption desorption barriers, they still stay fanned out. But we have this idea that just hiding in this is an ability to collapse these data. But hiding in this also is a chance to tune the rates. The highest my surface concentration can become is its maximum packing. The highest my bulk concentration can become is the CMC. So if I'm in a very dilute system, I can have a really appreciable depth. And I can go quite concentrated and diminish this depth. And so I can change the time scales for equilibration quite dramatically by playing with this length scale. And this is really the hook. This is the interesting hook where bulk-soluble surfactants allow you to tune behaviors. You're just playing around with a Langmuir model. We can just write this way, where K is this adsorption over desorption rates. And basically you can think about it as being proportional to your bulk concentration. At dilute bulk concentration, I have an upper bound, and at high bulk concentration, this can be driven to be quite small. And so we can go from millimeters to tens of microns. So we could go to a system where you're really diluting very significantly, or you're very weakly diluting. And that's below the CMC and above the critical micelle concentration. There are still lots of open issues, and I'll talk about that. So I've got this idea of this adsorption depth, which is going to be weighting my diffusion rates throughout the rest of the talk, and I still have this adsorption-desorption rates in the system. So above the critical micelle concentration, there's still discussion. So micelles are these aggregates of surfactants. For each surfactant system, depending upon your bulk concentration, you can have a tendency, for example, to form spherical micelles or cylindrical micelles, and the aggregation numbers for these entities are known. And so what's less known is precise information about their adsorption behavior. So there are two studies that I think are very interesting that reach opposite conclusions. And so I think that what the right answer is, the details of the chemistry matter. So in one study, a group formed an interface between, for example, an aqueous and oil system. And they arranged that the surfactant molecules were soluble in the oil, so they could be drawn away. So these micelles could approach the interface, surfactants could adsorb, and then the surfactants could desorb, so they could set up some fluxes, so they could study this over a prolonged period of time. And what they saw was they have a solution with a concentration above the CMC, and in these micelles, they've added a dye that fluoresces when it's hiding in oil. But if it's in contact with water, it's quenched. And so the molecules approach the region adjacent to the interface, the micelles, they break down and adsorb on the interface as monomers and then partition in. And under certain conditions, they could take images of a micelle-free zone. So for these systems, these micelles, which are tails inside, polar groups outside, beautiful little spherical aggregates with a certain well-defined number of molecules, they come adjacent to the interface, they demicelize into monomers, partition onto the interface and into the oil phase. In other settings, they stay intact. They stay intact. And so there's no evidence of micellar breakdown, and there are suggestions that the micelles themselves are adsorbing and tearing open at the interface. And so this has big implications for transport, just because the breakdown of micelles takes time. And so are they just going to slam into the interface and tear open, or are they going to go through this transport step? And I think that it depends. I don't have anything wiser to say about that either. Okay, so now I wanted to go back to hydrodynamics. So we have this idea. I'm going to scale my surface concentrations with its equilibrium value, which means it's going to then depend upon the bulk concentration. I want to scale viscous stresses just with this apparent scaling. I have some translational velocity, viscosity of one of my two phases. A viscosity ratio would appear otherwise. And my drop length scale. And I think about my Marangoni stress. And my Marangoni stress in this situation is just going to be within a sign, 1 over my drop radius, some theta derivative of my tension. And I'm going to use a chain rule. I'm going to say that that's going to be the derivative of my surface tension with respect to composition times my change of surfactants, absorbed surfactants on the interface. And within this model, I'm going to take the derivative, and I'll make this whole thing dimensionless, and I'm going to end up with something that looks like this. A number I'm going to call the Marangoni number, but it just has this prefactor RT gamma at infinity in it. I'm isolating the compositional dependence and making it explicit here. So I have a Marangoni number, my compositional dependence, and my derivative of my surface excess. And primes are used here and there, and I was not consistent. So this is a dimensionless quantity, but they won't always be primed. I apologize. Okay. This X is how close am I to maximum packing. And so if I'm really dilute and X is really small, then this doesn't matter. My number MA times X is going to be small, and I'll be weakly coupled. But if I start to approach maximum packing from below and x approaches 1, this coupling becomes really pronounced. Okay, so highly densely packed layers have a chance of being very highly coupled. But it depends, because I have this droplet, and remember, I have these mass transfer rules happening. And so the question is, what happens for soluble surfactants? So let me go through this a bit. I have this surface tension law now. I have a region of low tension that's going to high tension that occurs only if transport to the interface is slower than surface convection and transport away is slower than surface convection. And so this is all highly coupled with the mass transport, and then it's tunable. So I want to go now into different mass transport limits. So if I look at a surface mass balance, I can think of the rate of change of adsorbed surfactant on the interface as having some dilatational part. I'm going to focus for now on non-deforming drops. So this is just a flow tangential to the interface. There's some surface diffusion along the interface, and there are fluxes from the bulk. Again, scaling my surface concentration with its equilibrium, and I'll take a convective time scale, I can cast this in dimensionless form. And I can look at it at steady state, and it has this form. I have a surface convective term that's balanced by fluxes from the bulk. If fluxes from the bulk are very fast, I get some behaviors, and if it's very slow, I get other behaviors. So it all comes down to what is this characteristic rate of exchange with the bulk. And if we start with it being negligible, let's suppose that, many of the early sort of mysteries with surfactants happened this way. People would have some fluids that had sat around, for example, overnight. So they sat around for a long time. And stuff adsorbed on the interface overnight. And then you do an experiment over the next, say, 15 minutes, 20 minutes. And your system was so dilute that given time overnight, things had time to diffuse and come to the interface. But given time during the experiment, there was no time for exchange. It was just all too slow. Okay? So there's a way in which something that's a soluble molecule could act like an insoluble monolayer in terms of bulk exchange. Okay? So in that limit, the surface mass balance takes this super easy form. It says that the surface divergence of gamma Vs is equal to 0. Okay? And that ultimately requires that we divide our surface into two pieces. Either your surface concentration is finite or your surface velocity is finite. If surface concentration is finite, velocity is 0. If surface concentration is 0, velocity is finite. So in this picture, whatever was adsorbed on this interface when we started translating got swept to the trailing end and accumulated there. And at steady state, we have this simple balance. So again, I've neglected diffusive fluxes because they're typically weak when we have external flows, and adsorption, desorption rates or diffusion or transport are negligible. So this limit has been studied by many different people, and here's just a nice simulations that let us see this behavior. So here, for example, are regions on a droplet where the surface velocity was mobile. And here, at the trailing end of that droplet, is a region where surfactants have accumulated and the surface velocity is immobile. And so this was an unretarded flow, adding a little bit of surfactant. In this limit, a little bit more, and a little bit more. So these are simulations, but they're just showing that in this limit, you can indeed divide the surface into mobile regions and immobile regions. And when concentrations are high enough, we're limited to a stagnant surface. And so this is the origin of thinking about surfactants causing droplets to behave like no-slip boundaries. And so this is increasing surface coverage or surfactants in solution if we had allowed them to partition and then run this experiment thereafter. If instead we have molecules that are not unable to exchange with the interface. But they can adsorb onto the interface, be convected to the trailing end, and desorb. In which case, we would now equate our surface flux along the interface, again assuming surface diffusion is weak and at steady state, to our adsorption and desorption fluxes. Okay. In this limit, and casting this in non-dimensional form, I can get the following equation, that my surface convective term is balanced by an adsorption-desorption time scale. So BO number is this desorption coefficient times my drop radius over U, and BI1 plus K is that adsorption-desorption rate made dimensionless with convective scaling. And so if this thing tends towards 0, I'm back to stagnant cap. If it's order 1, I'm slow everywhere on the surface. And if I go to infinity, if I can make this really fast, if I take this BO number to become very large, I can force my surface concentration to its equilibrium value. Okay. So just simulations to look at that limit are shown here. Here's the surface velocity. Here is, with a very weak BO number, a very weak adsorption-desorption, we can see I have a surface velocity that's finite and some region where it's very, very low. That very, very low is because we're looking at a BO number of about 0.05. Okay. And as if we were allowed mass transfer to become faster than convection, I can restore the interfacial free flow. The thing is, you don't get to do that. You don't say, hey, I have molecules in solution and I have to work with this formulation and I would like to control the interfacial mobility, please. I'm going to keep changing my adsorption-desorption rate. If your formulation is fixed, it's fixed. So this is not a free parameter. You don't get to just vary your BO number. So then you could look at this and say, well, what if I take this concentration to become large? This is just beta C over alpha. It's a dimensionless form of the bulk concentration. If I take that to become large, can I force my surface concentration to its uniform value and restore free motion? But these nonlinearities are peppered all over this system. So if we look at, for example, just estimate our dimensional Marangoni stress, it's going to go as RT divided by 1 minus X, my fractional coverage, times my gradient in concentration. This is a measure of my gradient in concentration. Putting that in dimensional form, I just get this. Plugging that there and simplifying, I get something that looks like this. My Marangoni stress is going as that prefactor times something that at high concentration becomes order 1. So the answer here is no. No, even though you'll be forcing your surface concentration closer and closer to equilibrium, the closer, you still have the Marangoni stresses. It scales out that when we put this gamma into this formulation, this 1 minus X is punishing us and forcing us to stay coupled. So at high concentration, adsorption-desorption controlled surfactants are not going to let you restore free motion. And so if you take, for example, the terminal velocity of a droplet that's at being controlled by adsorption-desorption, and you vary the bulk concentration, you find you don't restore free interface flow. Here's free interface flow. Down here is Stokes' law. And you can reach some asymptote, but you do not restore free motion. So the nonlinearities for the adsorption-desorption control limit conspire to force you to remain coupled. If instead we look at diffusion control, if we look at diffusion control, then we see, I'm jet lagged. I looked there and thought I'd gone long. You all remind me. If we look at diffusion control, and again, we choose bulk equilibrium concentration, bulk concentrate, equilibrium surface coverage, bulk concentration, scale the velocities with U, scale gradients along the surface with the particle radius. And now I have to contend with diffusion fluxes. If I'm at high Peckley number, I have a diffusion boundary layer, and I have to scale this with A 1 over square root of P. If I'm at moderate Peckley number, I don't have that diffusion boundary layer. So that's sort of in parentheses, because I might have it and I might not. Okay? And I can equate this, and I can get this expression. If I had the diffusion boundary layers, this is the form. If I don't, it goes as 1 over Peckley number. Okay? But no matter what, I have this ratio A over H emerging. The H came out because I scaled this one with its equilibrium packing, this one with its bulk concentration. I can divide through, I get this adsorption number. This adsorption number, remember, is something I can tune. By changing the bulk concentration, I can tune how much I deplete solution, and I can make this time scale fast. So, again, if the right hand here is 0, I'm at a stagnant cap, and if I become infinite, I should have no retardation. Why? If this is infinite, then this surface flux is remaining finite. This thing has to go to 0. Okay, so here's some simulations done by Wang et al., where they're looking at a case where they had order 1 Peclet numbers. So their coupling went as 1 over Peclet, A over H. And it's, here's the surface velocity of a droplet that's moving in a surfactant solution, and the clean surface flow is just the sine theta over 2. And if they add a tiny bit of surfactant, this beta C over alpha of 0.01, they have a uniform retardation everywhere on the droplet. If they add a bit more, they see something reminiscent of these stagnant caps. If they add more, they have uniform retardation. But then if they add still more, they move their way back up to the clean surface flow. So the picture here is this. Surfactants are so plentiful that they can adsorb onto the interface rapidly because we're in a diffusion controlled limit. Adsorption is just local equilibrium. Because our adsorption depth has become very small, we can't deplete the region next to the interface. No depletion, no gradients. Similarly, because they can convect along the interface where they pop off in local equilibrium with the sublayer. But because because H is close to 0, we have no accumulation. So in this limit, we have this peculiar thing, a very surfactant-rich interface. Surfactants adsorbing, convecting along, desorbing, and all in local equilibrium, all without any Marangoni stresses. And so, if we look at the form for the surface stresses, and we say my surface stresses have this form, here it was written in the form of gamma equilibrium over gamma infinity, but I can recast that to be in terms of my bulk concentration. And that takes this form. And if I estimate each term, my delta C, my fractional change in concentration here decreases with bulk concentration. My change in gamma goes as 1 over k squared for high concentrations. And my change in Marangoni stress goes as 1 over k for high concentrations. So this conspiracy of solubility and the nonlinear law allows these diffusion-controlled molecules to be decoupled. So at very high concentrations, if compared to your surface convective fluxes, adsorption, desorption are rapid, then you move with a low surface tension, more deformable perhaps, but with no tangential stresses. So here, for example, are the simulated drag at that order 1 Peclet number as a function of this bulk concentration. And we can see that in all cases, the drag goes up, and then it comes back down again. This piece was completely anticipated in all the classical work. Surfactants will increase the drag to drive a flow. This piece was much less anticipated. Add a lot, and if the adsorption, desorption rates are fast, restore free motion. So this brings us back to other classical work, only in H. This is my PhD work. And so if we looked at say I had gas bubbles and a drop of liquid and a gas bubble and a drop of liquid and a gas bubble, and these are all being surrounded by a fluorocarbon oil and being drawn through at constant velocity through a train. And in fact, this was an early precursor for microfluidics devices. This was a sub-millimeter tube, quite similar in scale to many microfluidics devices. The industrial enterprise that paid for this had Mr. Jones's yuck in here, separated by a spacer, then Mrs. Smith's yuck in here, separated by a spacer, etc. And at that time, microfluidics devices weren't common. But foam-based mobility control, to be able to stop liquids from rushing through porous rock, was common. And what we all understood was that the Laplace pressure drops across these surfaces could be quite costly. And that if ever we had some slow flow on the surface of these droplets, that we would get Marangoni stresses, a surface velocity that differed from the wall velocity across a thin gap. And we should take divergingly large pressure drops to run. But the company, well, they had to make money. And so they just tried stuff. They tried stuff, and in fact, they found this answer. And they came to us and said, why? So they found that they could run this system at very low pressure drops. And they could have many repeat units. It was just spirals and spirals and spirals of Teflon tubing. And they would have various markers along the way. It was a spectroscopic analysis. And so here, every now and then, instead of Mrs. Tekatak's stuff, they would have a marker to say, here's where we are in this train, to make sure they didn't lose count. And they would be doing continuous flow analysis of different biological assays. And so in this flow field, the question was, what happens and why? And so the finding is, and it's kind of not fair because they guided us to it, that the pressure drop in this system normalized appropriately. But the pressure drop in this system, as we add a surfactant with fast adsorption kinetics, becomes elevated compared to a clean surface flow. Then you add more and it drops. And you add more still and it becomes restored to free motion. And in fact, in many cases, it was below the clean interface flow, because clean wasn't really clean and there were surface active impurities. In which case it starts to be tempting. Just throw in a lot. Throw in a lot of whatever is your surfactant and hope. But it doesn't work. If adsorption and desorption aren't fast compared to your convective timescale, it doesn't work. And so, for example, if you throw in lots of proteins, these things become impossible to drive. Okay? But if you throw in proteins with these surfactants that can dominate the interface, that can have they're swampingly present. Realize what we did. We put so many in that they're adsorbing and desorbing everywhere along that droplet, and we can never make a gradient. And by having them present in such high number, the proteins also never stood a chance, statistically, to get to the interface. So thermodynamically, they were favored, but kinetically, they never got there. And so if I add a protein, the protein pressure would start somewhere up here, and for example, low. Suppose I'm adding protein. It comes up from down and then goes to some value, and it never comes down. If I take something that had a lot of protein and add this molecule, I have something that goes. So you could use surfactants as additives to protect the interface, to stop the adsorption of Mr. Jones's proteins, and make sure there was no mischief with Mrs. Smith down the line. And that was a big issue that actually ultimately challenged these assays for use in many medical diagnostic settings, was concerns about partitioning into the fluorocarbon oil and cross-contamination. Okay. So this is it. This is the first hour. We can control stresses. And if we can control stresses, we can do things. And we can do things like run microfluidics devices with slugs of liquid that can be put in very small tubes in very challenging situations. And so all of that thinking is sort of a surprise when you think about it. If we started out thinking that, and in fact, look at this. If I go over the scaling for this, it looks a lot like the scaling we had previously, except diffusion transport takes over the radius, and convective transport goes over that length. So the time that we have to go to this trailing stagnation ring goes as the length of the slug over the velocity. And since the slug was really long compared to the radius, that also gave us all the time in the world to be able to restore free motion of this system. So the counterintuitive thinking here is also, by lengthening this slug, it became easier to control the pressure drop in this system. Smaller droplets were not better. You wouldn't have guessed that a priori because it's a thin film region here. Okay. With that, I'm going to stop. In the next hour, we'll talk about deforming drops.
Okay, then we'll stop until 2:45, and then we'll have another hour.